material, which is true, but the way I thought about it is like this. You know, I'll do all the problems in this, or at least look at them, and then kind of focus on the more challenging problems. This way I get up to speed a lot faster, you know, rather than struggling on some of the more basic ones. You know, just work on these, or because typically what happens is you get hit with very challenging problems on the test. Sometimes much more challenging than what's in the homework. So. Well, anyway, we'll just start off with this approach, but I don't have time to go through every single one. But we'll just look at them quickly and see if there's, you know, some of these are just repetitive. Except write an equilibrium constant expression Kc for the reactions. So this would just be all concentrations here. But when we look at this, these are all gases. So normally when we have gases, do we use a Kc or Kp? We use a Kp. Is it okay to use a Kc? Yes, it's going to be a different number. Kc and Kp will be a different number if delta N of gas is not equal to 0. And so here, what is delta N of gas? Can you see it? Yeah, we start off with 3 moles, we end up with 2 moles, and it's -1 minus 1 mole of gas. And so Kc and Kp are not equal. And then we have Keq. Keq for reaction A here would be equal to Kc, Kp, or neither. Yeah, in this reaction, Keq, which would be the thermodynamic equilibrium constant based on activities, would be equal to Kp. And neither of those is equal to Kc. Sometimes solids throw people off. What's the activity of solids? 1. So those fall out. Here we have a solid. If we have pure liquids, the same thing happens. And here's Kp. We write Kp for this. It's fine. Kp for this. And these are solids here, so we can write a Kp out for this. H2O goes to gas. Problem number 5 is looking at formation from the gaseous elements. So these are like formation reactions. 1 mole of HF from the elements. 2 moles of NH3. Normally formation reactions are per mole of substance. So this would be 2 times the formation reaction. So just looking at formation reactions. Number 6, write an equilibrium constant Kp for the formation. So just more formation reactions. All right, these are some Kc, Kp conversions. And so here we just need the equation. Kp is equal to Kc times RT, that quantity raised to the delta N of gas. So it's just getting practice looking at delta N of gas here. What's delta N of gas here? Yeah, +1. We go from 1 to 2 here. -1 here. 0. Does everybody see this one's 0 because this is solid, that's solid. So we're going from 3 moles of gas to 3 moles of gas. Delta N of gas is 0. So in this case, there's no calculation necessary because Kp is equal to Kc. Here. For the others, Kp is not equal to Kc. And so we can look, you know, Keq, the thermodynamic, would be equal to Kp. So Kp is equal to Keq, which is not equal to Kc here. Here, Keq would be Kp. Here, Keq would be equal to Kp in most cases. All right, and here we're just flipping around. Now we're going to solve for Kp from Kc values. So they give us Kc values. We just got to figure out what delta N of gas is and plug it into the equation. Well, let's do an example of this. Number 9, the vapor pressure of water at 25 degrees C is 23.8 millimeters of mercury. So here, vapor pressure of water. So number 9, vapor pressure is given by this equation. H2O liquid goes to H2O gas. And the vapor pressure of water at 25 degrees C is equal to 23.8 millimeters of mercury. Write Kp for the vaporization of water with pressures in atmosphere. Okay, so this is what's given. They want us to figure out what Kp is. So what is Kp based on this? Kp would be the partial pressure of the products over the partial pressure of the reactants. Partial pressure of the products would just be the pressure of H2O gas. H2O is a liquid, so that would just be 1. So this would just be the partial pressure of H2O gas. That would be Kp. This Kp value, well, here's the pressure right here. This Kp value is 23.8 if the units are in millimeters of mercury. But what they want us to do is they want us to get Kp with pressure in atmospheres. And so if this is the Kp, the ratio in millimeters of mercury, to go for atmospheres, we just convert millimeters of mercury to atmospheres. Now, Ks are usually dimensionless. So this is why I put this in parentheses, because normally we don't include a unit. But in this case, we have to know what the unit is, because we'll get a totally different K value if this is in atmospheres. Because if this is in atmospheres, our K value is going to be what? So an atmosphere is 760 millimeters of mercury. And so we'll just take 23.8 divided by 760 gives us 313. And so take a look. If we express the pressure in millimeters of mercury, we get this ratio, 23.8 to 1. If we express the ratio in atmospheres, we get this, 0.031. Do you know if we express this in bars, what the ratio is? You might remember this, because you've seen it before. It's almost the same. Rather than 0.031, it's like 0.032. I made that mistake earlier on the practice test. And so we have to be aware, of which one. Normally we were working under which of these units in terms of bars. So this would be a 0.032. And that's because of Appendix D. So that's the Kp. Now, what is the value of Kc for the vaporization process? Now, we know that Kp and Kc are related. Kp is equal to Kc times RT raised to the delta N of gas. And so Kc is equal to Kp divided by RT raised to the delta N of gas. And so we need to know which R we're dealing with. What R are we dealing with in this case? It depends on the units. Which units are we dealing with? We're dealing with atmosphere. And based on the derivation of this, where did this come from? This equation? This equation came from the... So which R do we use? Do we use the 8.3145 or do we use the 0.08? 0.08, yeah. That's because this derivation came from the ideal gas law. And so this is going to be Kp. Now normally, do we do units in the Ks? We don't do units. Why? Well, one, the units always come out weird. You might get molarity squared or atmospheres cubed or something like that. The units always come out weird. But that's not the reason we ignore the units. Why do we ignore the units in K? It has to do with the activities. What's special about the activities? What's special about the activities is the activities don't have units. Activities are dimensionless. And so these Ks are actually dimensionless. And so normally we don't deal with the units, but in this case I might consider the units. Because the units are going to make a difference in what R we use. Like in Chem 4, they teach you, they make you memorize like 3 different Rs, depending on the units. So they have an R if you use millimeters of mercury. They have an R if you use milliliters. So many different R values. It gets all mixed up. It's much easier just to memorize one and then convert it to whatever units you want. And so which R do we, well, since we're using atmospheres, not bar, I have the one for atmospheres memorized, 0.08206 liters atmosphere per mole Kelvin. This is the R we use. Times T will be 298 Kelvin. Okay, we're going to raise this whole thing to delta N of gas. What is delta N of gas for this? What is it? 1. And so, and if Kp is in atmospheres, which is going to be in atmospheres essentially because it's 0.03131 atmospheres, then the atmospheres will cancel. And leave us with 1 over liters per mole, which gives us molarity. Okay. So let's calculate it. I'll take that divided by 0.08206 divided by 298. And so if this were in terms of Kc, would be 0.00128 molar. That would be the molarity of the H2O gas. Since it is a gas, molarity is going to be low above the liquid. All right, if we continue on at Kc, it's 5.12 times 10 minus 3 for the equilibrium established between liquid benzene and its vapor. What is the vapor pressure of benzene? And so this is the same thing. We convert Kc into Kp. Now, when we think about this Kc, what would the units of this Kc be? Because we essentially the same type of problem. We're going from liquid benzene to gaseous benzene. So the units of this Kc should be in terms of molarity. The activity of gaseous benzene would be equal to the molarity of it. And so we're just going to convert from molarity into atmospheres. Oh no. Probably the easiest would be converting molarity into, actually, if this were, if they don't tell us if this is under bar or what is this? Well, we could go from molarity into atmospheres, assuming, and then from there we could go into millimeters of mercury. This one is doing bar. All right, then we have these type of problems are different. This is deriving or determining K's, and so far the types of problems we looked at, one, just generating the K expression, the ratio up here, and then 2, conversion, Kp to Kc, and Kc to Kp, and then 3, determining K's. But we determine the K's not by measuring the equilibrium concentrations experimentally. We determine K's by using Hess's law. And so did we do this problem number 14, I think it was? We did this, finished? Okay. And so, or was it this one? No, number 12. That's it. We did this one. And so this is just, we want to determine the K for this reaction here, but we don't have it. It's unknown. But if we're going to add up these in some way, so that when we add up these equations, we get this as a net equation, then we can determine the K's. And so you add the equations. What do you do with the K's? You add the K's. In chapter 7, we added or combined or summed up the energies, but in this case, we don't sum up the K's. We multiply. And so that's using Hess's law type application for this. And then we have these 2 problems at the end here. An important environmental and physiological reaction is the formation of carbonic acid from carbon dioxide and water. So let's take a look at that. So if we look at 15 here, this is carbonic acid formation. H2O liquid plus CO2 gas goes to H2CO3. Okay, write the equilibrium constant expression for this reaction in terms of activities. So we do this one first in terms of activities. So KEQ, it's in terms of activities, will be the activities of the products raised to the respective power. So the activity of carbonic acid, AQ, raised to the first over the activity of H2O liquid, raised to the first over the activity of CO2 gas, raised to the first. So this would be the activities here. Convert this expression into an equilibrium constant expression containing concentrations and pressures. So we know the activity of the solution is roughly equal to the concentration of that solution. So it would be H2CO3. The activity of a pure liquid is 1 times the activity of a gas is just the partial pressure of that gas, CO2 gas. And so it would just be equal to the concentration of carbonic acid over the partial pressure of CO2. This equilibrium is heavily favored on the left. Carbonic acid is quite unstable, so the product unstable reactants are going to be dominant here. 16 is kind of similar. This is equal to KEQ. Now, is KEQ equal to KC? Is KEQ equal to KC for this reaction? No. Is KEQ equal to KP? No. And so here's a case where KEQ is not equal to KP, which is not equal to KC. All of them have a different number. In fact, we wouldn't use a KC for this. Well, actually, we could. I suppose we could if we get the pressure, rather than the pressure of CO2, we get the concentration. We can't do KP. I mean, there wouldn't be a KP for this because carbonic acid is not a gas. We aren't going to be measuring the partial pressure of this in that case. All right, let's take a look at the next one here. Rust is caused by the oxidation of iron by oxygen. So 2 iron solids plus 3 halves O2 gas gives us Fe2O3 solid. Now this reaction is going to be heavily favored to the right. This reaction is heavily favored to the left. And so when we look at this reaction, the K should be big value. This reaction, the K should be a small value, much less than 1. This one should be much greater than 1. Indicate the ratio. And so write the equilibrium concentration, in terms of activities, and then in terms of concentration of pressure. And so this will be the activity of Fe2O3 solid divided by the activity of Fe solid squared and the activity of O2 gas to the 3 halves. What chapter was activities in? If you wanted to review activities, what chapter would you look at? Do you recall which chapter activities are discussed in? Activities are discussed in chapter 14. And so this is another thing they had to do because it was more thoroughly discussed in chapter 14 in the solutions chapter. There's like 1 paragraph in there. And then they did a little intro in chapter 13 as well. Anyway, going back to this, this is just going to equal activity of solids 1, activity gas, pressure of gas 3 halves. So in this particular one, KEQ is equal or not equal to KP? Actually, KEQ is equal to KP in this case, but it won't be equal to KC. So these are the types of things we should be able to do up to this point after 16 when you look at all these problems. All right, did we do number 18 in class? Forgot where I stopped. No? We started it? Okay, this is experimental determination of equilibrium constants. And so number 17 is very similar to number 18. We'll just do number 18. Skip 17. So sometimes you can't avoid doing an experiment. You know, it'd be nice if we had Hess's law. You know, we try to find reactions similar to this and try to combine them to get this as a net reaction. Then we can avoid doing experiments. But if you can't do that, then we'll just do the experiment. For number 18, we're looking at the reaction 2 hydrogen gas plus S2 gas. That's 2H2S. Gaseous state. But whenever we do a Chem 1B type problem, like the reactions or stoichiometry type problems like this, we usually set up an ice table. And so what's given here? There's KC or KP. Actually, KP is not even given here. They want us to figure out what KP is at 1670. Well, in order to determine what Kp is at 1670 Kelvin, then we need some information. This is going to be the ratio of the products, so this would be H2S gas squared, or the reactants, it would be H2 gas squared. This is diatomic sulfur, S2 gas, the first. And so what we need is we need the equilibrium pressures of each of these. If we know the equilibrium pressures, then we can just put those into this equation and solve for Kp. Did we already calculate the pressures? I think so. Yeah? I think we finished this, didn't we? No? We did finish it? Okay. Let's skip this one. I know I mentioned it before, but you know, and I use like the guide analogy for this is like the usually when you watch somebody who's been doing these for years, these kind of problems, they just weave their way through the problem, avoiding all the pitfalls, all the traps, all the dead ends, all that type of stuff, right? Because you've done it so many times, you can avoid making the common mistake. But somebody who's new to this is going to make those mistakes, usually, and they're going to end up in a lot of dead ends or traps or whatever else. And so the best thing to do is just to work it yourself. Like I said about the homework, I'll just look up the answer, but it's not just that, because what I would do, it's not just looking or memorizing the answer, but what I do is just kind of analyze it in my head. What are they doing here? Does it make sense to me? Would I have done it that way, et cetera, et cetera? And so when you watch somebody solve a problem, you're just following along, right, behind them. And so this is why I think for me this is like going to a jungle, unfamiliar jungle. You're in an unfamiliar jungle, but you have some natives there, and the natives are going to guide you through the jungle, and they're going to avoid all the dead ends and all the traps and all the pitfalls, right, because they know their way around. And then the next day you try it on your own, and then when you try it on your own, everything looks different, right? You know, each fork looks different. You know, before you weren't paying close attention maybe to the forks or the tracks. And this is like what happens when you watch somebody solve a problem. When you watch somebody solve a problem, it's the same thing. You're just, you don't have to pay attention. You know, they know the directions. And so this is why it's important. You should repeat the problems that we do in class. You know, just write out the initial and then blank sheet of paper, and then just see if you could repeat it, just like we did in class. You know, if you could repeat it just like we did in class without any help, then you got it. You got it down. And that's good. And it should give you some confidence for exams or whatever else. All right, and so these, you know, if you do 18, 17 and 19 are very similar to 18. You can see that by looking at them. Let's go on. 20, very similar. 21. 21 is different. 21 already has K. What homework section were we in? We're in this homework section, which was experimental determination of equilibrium constants. I know experimental determination of equilibrium constants. A bunch of problems. They're very similar, except when I get to 21. 21 looks totally different. That's because the K is already determined for you. And so we don't have to determine it experimentally. So what are they asking for here? Well, they're asking for something else entirely. And so write the equilibrium constant expression for the following reaction. Okay, that's not difficult. We could do that. That's similar to the first series of problems that we encountered. The first series of problems we encountered, this should be pretty straightforward. It's just FeOH3 solid, which they forgot. It makes a big difference, you know, if it's solid. I know this has got to be solid. Why? Because hydroxides are all insoluble, except for group 1 and ammonium. So it's just a typo, they forgot the solid. Plus 3H plus AQ goes to Fe3 plus AQ plus 3H2O liquids. And so they give us the K value. They just want us to write the K expression. So this doesn't belong in this section. This belongs in the first section. 9.1 times 10 to the third, which is equal to. Now, they asked for K. And so what does that mean? Are they asking for KEQ, KC, or KP? If they don't specify, what are you going to write? Should I write KEQ, KP, or KC? Because in the earlier sections, they specified which one they wanted, but now they're just saying this is K. It's got to be KEQ. And so they want the KEQ expression. The KEQ expression is going to be the activity of the products, so activity of iron 3 plus, activity of H2O liquid. On both, H2O liquid should be cubed over the activity of iron 3 hydroxide, solid, and the activity of H plus cubed. All right, then we're going to convert this into equilibrium constant, either concentrations or pressures. And so the activity of iron 3 plus is going to be just the concentration of iron 3 plus at equilibrium. And the activity of H2O liquid, it should just be 1 cubed, divided by the activity of the iron 3 hydroxide. The activity of iron 3 hydroxide is 1 times the activity of H plus. The activity of H plus would just be the concentration of H plus cubed. This would be the equilibrium. And so when I look at this, KEQ is equal to what? KC, KP, neither, both? Yeah. And so here, KEQ is equal to KC. All right, that's fine. And so we did that. Well, that belongs at the beginning of the homework section because that's a pretty easy problem. Right? Okay, but this second part, and compute the equilibrium concentration for Fe3 plus at pH 7. All right, now they want us to calculate the equilibrium. So rather than figuring out what K is, what we're going to do is we're going to use K to figure out what the equilibrium, concentrations are going to be. In other words, we're going to figure out the stoichiometry of this. Whenever we have that type of problem, I always set up an ice table. Your book won't set up an ice table for this, but I do. I just set up an ice table for all these problems. and then just look at all the variations that we have in what we're solving for. And you'll find there aren't that many variations, really. All right, so what do we do about this? Does the concentration of iron 3 hydroxide change over the course of the reaction? Does the concentration of iron 3 hydroxide change over the course of reaction? No. The concentration doesn't change, the amount does. For example, in this reaction, we're going to lose iron 3 hydroxide. So in all our problems in which we have pure solid or pure liquid, or both, what we assume is that there's plenty available. And so we aren't going to run out. In other words, the solid iron 3 hydroxide will not be a limiting reagent. We just have to have a little bit or a lot in there to maintain this equilibrium. And so what we do with pure solids is just draw a line through here. We aren't going to put any numbers here, even though I know that I'm going to consume some of it. If I want to figure out how much I consume, I do a separate Chem 1A style stoichiometry problem for that. I don't include these into a Chem 1B stoichiometry problem. But definitely I'm going to lose some of this. But it's not going to impact the ratio at equilibrium as long as I have some. Now H2O liquid, the same thing, H2O liquid, pure H2O liquid is 55.5 molar. That doesn't change if I gain some or lose some H2O liquid. And so I omit from the ice table no solids, no liquids. Only aqueous or gaseous species are going to be here. Now I got to plug in, the values here. So let's start off with H plus. The H plus they give us, the H plus concentration of 1.0 times 10 minus 7. Now this is going to be in molarity. Now, is that the initial or is that the equilibrium concentration? Well, they want the equilibrium concentration of Fe3 plus, so I need to find that. I need to find this, the equilibrium concentration of Fe3 plus. Equilibrium. At pH 7, and so the H plus they gave us here, is that H plus initial or H plus equilibrium? Well, they want the equilibrium concentration at this pH, and so that means that this has got to be the H plus concentration at equilibrium. And so at equilibrium we're going to have 1.0 times 10 to the minus 7 molar. And so when we look at this, the only unknown we have, we know what K is. We know what the H plus concentration is at equilibrium. The only unknown we have is the iron 3 plus. And so we just solve for iron 3 plus. And then we're done. So we can get it. And so this is just a Chem 1B style stoichiometry problem. Now what about the rest of the ice table? For this particular problem, we didn't need the rest of the ice table. We didn't need it. But we should think about it. It's just an aside. If we think about this as an aside, then typically what we do is we start off with 0. If we start off with 0 iron 3 plus initially, then we react some of this to form some, then we call this plus X molar. And so in this case, if we started at 0 and then we ended up here, then this would be the plus X, the number we would have calculated there. And so that tells us about the H plus concentration, because we need to end here. If we end here, that means the initial H plus concentration was here. And then we have minus, not X, but minus 3X molar. And so initially we had to have more concentration of H plus because we're going to use some of that, right? And we need to end at pH 7. And so this would just be an aside here, because what we're going to see is when we do a bunch of these calculations, this is going to be a common thing where they ask us to go backwards to figure out what we must have started with from where we end up at. In this case, well, we are already at the end. We're already at equilibrium, so it's just a simple calculation. Right? This. All right, now this is the same type of deal, 22. 22, they give us the K value. They just want to figure out the equilibrium. Concentration. So it's a very similar problem, 22. 23, did I talk about 23 yet? I did? Oh, okay. So 23 is a little, 23 we have two unknowns. If they didn't tell us what the equilibrium concentration of H plus is, they did here, but if they didn't tell us, we would be solving for the ratio. You know, one thing you don't say is, you never say, you know, you can't solve it, usually. What you do is you say, okay, this is what we can solve to. We solve it to an equation. Once we get an equation, then we see what that ratio is and see how it could vary. You know, typically we'll make an assumption. If we assume, you know, a very high concentration of H plus, a low concentration of H plus, then this is how it varies. So that gives a more useful answer sometimes, rather than just one value. So if you solve it to one value, it's only good at that one value. But if you solve it to an equation, then you can generate lots of values quite rapidly. We call these engineering style equations. Do we talk about 24? I don't think so. But we finished 23, is that correct? Yeah. All right, so going on to 24, for the dissociation of iodine at about 1200 degrees C, it gives the Kc value. And so this is just another variation of the ICE table. What we do is when I go through and I look at all these problems, I set them up all up the same way. I set them up with an ICE table like this and see all the variations of what I'm asked to solve. And so if I look at number 24 here, this is going to be the dissociation of iodine. So we start off with iodine gas. And iodine is going to dissociate into atomic iodine. This one, what's happening with the entropy in this particular problem? Entropy is increasing. And is this endothermic or exothermic in the forward direction? Endothermic. You have breaking bonds. And so this is going to be spontaneous at high temperature, non-spontaneous at low temperature. In fact, you know, in the sun has very, very high temperatures. Within the sun, do any molecules exist? What do you think? Is the hydrogen in the sun H2, or is the hydrogen in the sun H? Is it H2 or is it H? It's H. Why? Because it's too hot for molecules to exist. There are no molecules that exist in the sun. It's all atoms because of thermodynamics. You know, at very high temperatures, this is going to be favored entropically. Well, anyway, let's get back to this here. And so what we do is we start filling this out. What volume flask should we use if we want 0.37 moles of iodine, atomic iodine, to be present for every 1.00 moles of iodine at equilibrium? And so over here we have 0.37 moles, and we have 1.00 moles. But there's a problem with this. And what is the problem? Do you see?
Square the product.
Okay, but before I square the product, there's something else.
Divide by volume.
Yeah, because you know, in an ICE table like this, I can either have molar or molarity or pressure in atmospheres or bars. I cannot have amounts unless, you know, the rate, it's a two goes to two equal molar amounts on both sides. And so this is the amount. I'm not allowed equilibrium amounts. I need equilibrium concentrations. And since amounts aren't good, let's go ahead and figure out the concentrations of this. Oh, actually, I don't know the concentrations because in order to get the concentrations, I need the volume. And so if I go to equilibrium concentrations, and this is going to be 1.00 moles divided by the volume, whatever that volume is, at equilibrium. This is going to be 3.37 moles divided by this volume. Now the volume is going to make an impact on the ratio, you know, because volume makes a difference in this particular case. So we have Kc is equal to 1.1 times 10 to the minus 2, which is going to equal, well, it's Kc, so it's going to be the concentration of iodine at equilibrium squared divided by the concentration of I2 at equilibrium. And so we could just plug this in here and solve for B. So this is 0.37 over B squared. This is going to be 1.00. Now the units aren't going to quite cancel out, I think. But, oh, actually they do in this case. Sorry, this is not square. This is square. And then solve for B. All right, it's another case where they gave us the initial. We can do an aside again, you know, because when we try to analyze these ice tables, like for example, you know, normally at a lower temperature there would be 0. If this were 0, let's just assume, you know, initially we had none. If this were 0, then what is my x value? This would be minus 2, actually plus 2x here. This would be minus x. And so my initial here of iodine would be 1.00 moles over V plus x. And so if I get 1.00 moles over V plus x, and I do minus x, then I'm at 1.00 moles of V to fill out the rest of the table. And, this is something that we think about when we're doing these types of problems, is filling out the rest of the table. But it's an aside because we don't have to. And in fact, the book completely skips. They don't do the table. Let's just go straight to that usually.
So if you increase the volume on that one, would you push it to the right?
Okay. If I increase the volume, this should shift to the right.
Okay.
A bigger volume is in favor. Le Chatelier's principle. It changes something called Q. Q's the given. In the Ostwald process for oxidizing ammonia, let's take a look at ammonia. Ammonia, is that electron rich, electron poor? Neither. What do you think? NH3. Well, what are the oxidation states?
H1 is plus 3 and N plus 3.
Yeah, okay. H is plus 3?
Or it's plus 1 each.
Plus 1 each. Oxidation states are not the total charge. Oxidation states are just the individual charge. And so some people will take the total charge, plus 1, plus 2, plus 3, and call that the oxidation state. That's not the oxidation state. That's the net positive charge. And then N would be minus 3, so the total minus charge would be minus 3 plus 3, which should equal 0 in this case. It's a neutral molecule. One time I was looking for ammonia. I was looking in a European chemical catalog. I couldn't find ammonia. They didn't have ammonia. So I was about to give up. I couldn't believe a large chemical manufacturer didn't have ammonia. But they did. They called it something else. They called it nitrogen trihydride. And so that's why I couldn't find it, nitrogen trihydride. But is it really a hydride? Well, it is in the class of hydrides. For example, methane's sometimes it's called carbon tetrahydride. You know. But really, is this a hydride? No, because hydride would be a hydrogen with a -1. And I know the hydrogen should be +1. Why is the hydrogen not the negative species in ammonia? Here's a review. Well, some people will say, you know, the rules. I'm just following the steps. The steps for determining oxidation state. If I follow the steps for determining the oxidation state, then hydrogen comes out +1. And therefore, since I'm following the rules, hydrogen's +1 rather than -1. Is that good? You know, because you have people who understand the rules, right? And who can apply the rules. And they say, oh, that's easy. It's really easy. Hydrogen +1, nitrogen -3, according to the rules. But then you start asking them, you know, the reasoning behind that particular rule. Don't know. And so when I look at the rules for oxidation states, this is what I get. The rules for oxidation state, this is my summary of the rules for oxidation state. I sum it up like this. The most electronegative elements get the preferred charge. You know why? Because they have the strongest pull for electrons. And so it's because of nitrogen. Nitrogen is much more electronegative than hydrogen. Although hydrogen's position is a little off because hydrogen in the alkali metals and the halogens. And so its actual electronegativity is halfway between. This is more electronegative than boron, less electronegative than carbon. Somewhere there, 2.1. And so hydrogen is no slouch, but nitrogen is strongest. So we'll give it to nitrogen. All right, so we're looking at the Oswald process. What are the possible products? The possible products are N2, N2O, NO, and NO2. This is a series for nitrogen. And which product do we generate? Which product we generate depends on how powerful an oxidizer you react with ammonia. You know, ammonia is pretty easy to oxidize. Ammonia would be a good fuel. In fact, they use something that looks very similar to this. Have you seen this? N2H4? It looks very similar to ammonia, right? But N2H4, this is rocket fuel. This is called hydrazine. And so hydrazine is rocket fuel, liquid rocket fuel that they use in rockets. But anyway, ammonia is good fuel. We can oxidize nitrogen from -3 to 0. What's the oxidation state of nitrogen in nitrous oxide? +1. In nitric oxide? And in nitrogen dioxide? So it depends on the oxidizing conditions. We use this symbol for oxidation or oxidizer. And so we do mild oxidation. If we do mild oxidation, we end up here. If we do strong oxidation, we should oxidize it all the way to here. But usually, you know, it's tough to predict, you know, and so then oftentimes we'll end up with a mixture of products here. And so they just show one possibility. Well, you know, normally what we do is, if we don't know where it's going, we just say it's going to go. You know, if you don't know where it's going to stop, you might as well just oxidize it all the way into NO2. But that doesn't always happen. You know, for example, did I talk about combustion of nitrogen? Is nitrogen a good fuel? No, it's not a good fuel, but it can be oxidized. It's going to be really hard to oxidize this. One way of burning nitrogen is actually, did you drive to school? You drove to school or took the bus or something like that, then you burnt nitrogen. You burnt nitrogen in the engine. Because the engine, the automobile engine gets to extremely high temperatures, and you need that you need the high pressures there, high temperatures to get this to go. And when we burn it, it could form, dinitrogen monoxide, nitrogen monoxide, or nitrogen dioxide. In other words, it forms a mixture of these things called NOx. Those NOx are eventually oxidized in air. For example, nitric oxide, this is a component in smog, this is a brown one. Actually, nitrogen dioxide is a component in smog, sorry. Nitric oxide is what's produced initially. This is colorless. Nitrogen dioxide is brown. So even if we form NO, eventually it becomes oxidized to NO2. Same fate awaits N2O, I think. So we get NOx. Well, what is this? So we have one possibility is this. This forms nitric oxide. It's a Kp value. Wow, 10 to the 19th. Is that favorable? It's favorable. That tells us ammonia is a good reducer or a weak reducer. You look at that K value, what can you conclude about ammonia? Is it a strong reducer, weak reducer? What would you conclude? I'd conclude it's a strong reducer. Look at that, 10 to the 19th means this reaction is very favorable. Yeah. Well, anyway, they give us for the decomposition NO2, what do they want us to do? They want us to write a chemical equation for the oxidation of ammonia to NO2. So we're going to oxidize ammonia all the way to NO2, except we don't have it. And so this is out of place. I mean, we can get it because this equation has NO2 and NO. And so if we add up these two equations so that we get NO2 as a product, then that's Hess's law. And so this doesn't belong in this section. This belongs in the Hess's law section way back at the beginning of the homework set. It's out of place here because, well, all we have to do is reverse this one. If we reverse this one, what do we do to the K? We invert it, and then that's it. Then we just add these two together. When we add these together, we multiply the K's and we get the Kp for the equation that we have written. And so 25 doesn't belong here. 25 belongs in the Hess's law section we saw earlier. So we continue on with these problems. We go to 27. 27 is different than the earlier problem. The earlier problem with volume, we see the volume did not cancel. In this case here, our ice table can either be in moles or it can be in molarity. It makes no difference. The reason is because if we look, we have equal molar amounts on both sides. So we have 2 moles of gas on the left, 2 moles of gas on the right. And so in this case, we're going to get, volume squared, 1 over volume squared. Over here we'll have 1 over volume squared. So if we got volume squared in the numerator and volume squared in the denominator, the volume cancels out. And so we can show that Kc is independent of the reaction volume and just depends on the moles here because we just get moles of carbon monoxide over V times moles of H2O over V. And so also Kc and Kp are going to be equal. Delta N of the gas is equal. This is just looking at, Kp is 23.2. And so explain which of the following situations might be found at equilibrium. Well, A won't. If A was found at equilibrium, then Kp should be 1, not 23.2. B, so this is a partial pressure of hydrogen and H2O. That doesn't make any sense. It's a ratio of products over the reactants. C, this is a product over reactants. Yeah, that makes sense. C is right. CO2 and water, that's wrong. That's mixing. product and reactant. And so this is more of a beginning problem. What is the K expression? All right, now we're getting into ice table calculations, you know, the stoichiometry. So here we're given a K value, and we're given some initials, and then we just got to figure out the equilibriums. So we've already done some of these. In fact, we're going to spend most of our time looking at these types of calculations. But before I do that, I want to show you some tricks to doing it. Number 40 is a little out of place. Number 40 is actually a challenging problem. Number 40 is a Le Chatelet shift problem, but we've got to do it quantitatively. In fact, we're going to change the volume and quantitatively see how this is going to impact. Yeah. Obviously, if we make the volume bigger, this should shift to the right. We're going to see that here calculated. So 40, we're going to come back to that. These Le Chatelet problems, qualitative, are pretty easy. Most people find those pretty straightforward. Okay. All right, now let's take a look. For the most part, these ice calculations just involve algebra. We've been doing a lot of algebra, but sometimes the algebra gets very difficult. And so we need to have some additional tools in order to solve these, like number 90. So let's take a look at that. Although number 90 you could probably do brute force. Let's eventually solve for an answer. But there's certain things you can do to make it easier. And so let's take a look at this one. We're going to look, whenever I have a problem like this, I just set up the ice table just for 2Fe3 plus A2. Iron 3 plus mercury 1 ion. This is going to be an equilibrium with 2 iron 2s and 2 mercury 2s. It's a similar type deal. Then we look at the K value. I always look at the K value. Look at the magnitude of the K. Kc is equal to 9.14 times 10 to the minus 6. 10 to the minus 6 tells me that we bias towards the reactants or products, let's say. Well, minus 6 would be a very small ratio, reactant. Biases towards reactants. But they give us, initial concentrations. So we have the first row, I. For I, the reactants are going to be at 0.5 thousand molar. And the products are going to be at 0.03 thousand molar. Now, this is your standard Chem 1B stoichiometry problem. What we want to do is we want to figure out, given these initials, what's going to be the equilibrium concentrations. And we're going to use K to help us figure that out, because Kc here is going to be the iron 2 concentration squared times the mercury 2 concentration squared. These are going to be equilibrium. Divided by the iron 3 concentration squared and the mercury 1 concentration. The first. All right. And so one series of problems in the homework, which I skipped over, but we already kind of did this. It's called direction of chemical change. Direction and extent. Extent of chemical change is figuring out the ice table, how much it changed. The direction we need to figure out. The direction is this. The direction is, I look at this ratio, and this ratio looks like 1 to a million. 1 to a million. If the ratio is about 1 to a million, it's not exactly, because on the numerator it's to the fourth, and the denominator is to the third. But if it's about 1 to a million, does this look like the proper ratio? No, it doesn't. But it's tricky again because it's nonlinear. Now, looking at this, what we need to do is we need to solve for Q. I need to know what my ratio is right now because, you know, I don't know. This initial ratio might already be the correct ratio. You know, my initial ratio might be 9.14 times 10 minus 6, which means I don't even have to bother solving the ice table because it's already the correct ratio. That doesn't usually happen. What usually happens is the ratio is too big initially or the ratio is too small initially. Most people are biased towards the ratio is too small initially. If the ratio is too small initially, then we need more product. That means this is going to be minus 2x minus x plus 2x plus 2x. You know, because we need to form more product. So we got to lose reactant, form more product. How much more? I don't know. Or if the initial ratio is too big, then if the ratio is too big, we have too much product. So we've got to back off on the amount of product. If we need to back off on the amount of product, we've got to form more reactant. So this is going to be plus 2x minus 2x minus 2x. And so I don't know if it's minus minus plus plus or plus plus minus minus. You know, I got to figure out the direction of the chemical change. In order to figure out the direction of the chemical change, I'll just calculate my Q. Now my K is the equilibrium. This is what the ratios should be at equilibrium. Q is just whatever you're given, the ratio that you're given. The ratio that we're given here is just the initials, 0.03 thousand. This is going to be squared. And this is 0.03 thousand squared. Well, 0.03 thousand squared times 0.03 thousand squared gives me 0.03 thousand to the fourth. Divided by 0.5 thousand squared and 0.5 thousand, and that would just be 0.5 thousand cubed. 0.03 thousand to the fourth, 0.05 thousand cubed. And so let's go ahead and calculate that. Oops, I have my calculator here. 0.03 to the fourth divided by 0.5 cubed. .480 times 10 to the minus 6. Actually, it's not that far off. You know, when you look at this, our ratio should be 9.1 roughly. We're at 6.5 roughly. And so it's a little off. Is it too small or too big? Our current ratio. Q is our current ratio. Is our current ratio too small or too big? Too small. Our current ratio is too small. I need to make it just a little bit bigger. In other words, I need more product. And so the direction of change is given. It's got to be minus 2x minus x plus 2x plus 2x. I got to make it a little bit bigger. And so over here, this is going to be 0.5 thousand minus 2x, 0.5 thousand minus x, 0.03 thousand plus 2x, and 0.03 thousand plus 2x. Okay, then what do we do? Well, what we're going to do is, okay, so this is too small. Our current ratio was too small, therefore we had forward, you know, as the direction of change, that is, we had to have forward reaction occur. So we lose reactants, gain products. All right, let me erase this here. Now let's solve for K. Oh, actually, we don't have to solve for K. We have it here. We have to solve for X.
Well, let's solve for x. 0.03,000 plus 2x. Okay, this is going to be to the fourth divided by 0.5,000 minus 2x squared and 0.5,000 minus x. The first. Okay, now all we have to do is solve for x. Okay, and so go ahead and solve for x. I'll give you a few minutes.